Okay, this is A2Further Maths. We are in Unit 6. We're looking at differential equations, and this is doing our introduction into second order differential equations. So if we take a look at this one, first of all, we're going to let the right hand side equal 0. You can see that there, and then we'll kind of deal with it whenever it's a function of x. But the standard form then of our second order differential equations is a d2y by dx squared plus b dy by dx plus cy equals 0. The nature of the solution, as in what the solution is going to be, is dependent on the sizes of a, b and c, as we frequently call it then the AQE, which is the auxiliary quadratic equation. If we let y effectively be d2y by dx squared, let it be m squared, dy by dx is our m, and then our y then is just going to be our 1. Then am squared plus bm plus c depends on your values then that you would get out for m. So as you know, with quadratic equations, there are three possible options. Either there are two distinct roots, and that's where the discriminant then is greater than 0. So if b squared minus 4ac is greater than 0, the general solution then will be of this form here, where it's ae to the alpha x plus be to the beta x, where alpha and beta then are your two roots, the two real roots. So say for example we have this one, d2y by dx squared plus 2dy by dx minus 15y equals 0. If you separate that out, then it's going to be m squared plus 2m minus 5. This one factorizes fine, and you get m plus 5m minus 3, so it's m equals minus 5 and m equals 3. So our general solution then is going to be ae to the minus 5x plus be to the 3x. We can work out our constants a and b if more information is given. Say for example you're told that y is 5 when x is 0. We would substitute that in, then we can find our a and our b. And dy by dx then is minus 5 ae to the minus 5x plus c be to the 3x. And when the dy by dx is 23 and x equals 0, again you can't see this, we can sub it in and get 23 is minus 5a plus 3b. This gives our answer then of a is minus 1 and b is 6. So their particular solution then y equals minus e to the minus 5x and 6e to the 3x. That's type 1, where b squared minus 4ac is greater than 0. Type 2, if we get a repeated root or two identical roots, obviously then the discriminant equals 0 in this case. So the general solution in this case is y equals ax plus b, all multiplied by e to the px, where p then is a repeated root in that particular case of the AQE. So our example here is 4 d2u by d theta squared minus 12 du by d theta plus 9u equals 0. Gives us 4m squared minus 12m plus 9, and that's 2m minus 3 repeated. So our value then of m equals 3 over 2. And that gives us y equals a theta plus be to the 3 over 2 theta. So you substitute in for your p there, whatever that root is there. Further information needs, and we can work out a and a b, a bit like our last example. The third type then is if we have complex roots, and that's where b squared minus 4ac is less than 0. If that's the case, then our solution will be of this form here. Y equals e to the px, a cos qx plus b sin qx, where p is the real coefficient and q is the imaginary coefficient of the AQE. So let's take a look at this example here. d2x by dt squared plus 6dx by dt plus 10x is equal to 0. We take out our AQE, which is m squared plus 6m plus 10, and we solve it. 36 take away 40, so it looks like we're getting complex roots, and our complex roots then are 3 plus or minus I. The important bit here is the 3 and the 1i, and the 3 then goes in here for minus 3, so that'll possibly be a 3, and then a 1 goes in there for those values there. With more information, oh yes, that is a minus 3 there, and that should be a minus there. Just trying to work out where we were going wrong there. So that should be a minus in there despite how it looks. So it's minus 3 goes to there, and then we have our 1 there for our I. With more information, a unique solution can be found. Given that x is 0 when t equals 0, we can have 0 equals 1 upon a cos theta plus b sine theta, hence a equals 0, hence x, therefore a equals 0, hence x equals e to the minus 3tb sine t. The x by dt, then if you differentiate this one here, you end up with this, and can find the information. We're then to our next page, equals b e to the minus 3t cos t minus 3b e to the minus 3 sine t. And t equals 0 whenever dx by dt equals 1 is what information we can give. We find then that b equals 1. So the particular solution is then x equals e to the minus 3t sine t. Just a wee summary then. So to solve a differential equation of the form a d2y by dx squared plus b dy by dx plus cy, we write down its AQE, that's its auxiliary quadratic equation in this form here, and solve it. You have three possible options depending on the nature of the roots. If it's two distinct roots, alpha and beta, then the form looks like this. If it's identical roots, still real, it appears twice, so m equals p, then the p goes in here. And if we have two complex roots, we have the p, which is the real part of the complex root, and then the q, which is the complex part the imaginary part then of the complex root, and we end up with that.